Hello and welcome back to another lecture. So in the last video, we put forward the concept of flip-flop, and I told you that the difference between a latch and a flip, both are memory elements, both are capable of storing 0 and 1, and later on retrieving of 0 and 1. But the manner they differ is basically how they react to the clock. Like I said, latch, by definition, it's imperative, it's implied that it will always be level sensitive, right? So that kind of adds ambiguity that it can actually trigger at any instant during the positive edge of the clock. But flip-flop is a refinement of latch in the sense that it is edge triggered, in the sense that it can trigger only at the edge points when the clock actually rises from 0 to 1. We also discussed how to achieve edge triggering, like the one of the very useful configuration is the master slave configuration, wherein we use two latches to construct a flip-flop. Anyways, today we'll be discussing a JK latch or a flip-flop. Like I said, functionality is the same. They both store bits. It's just the manner they react to the clock. And JK latch or the flip-flop, it is a refinement of the SR latch in the sense that the indeterminate state, remember the indeterminate state in the SR latch, wherein if the inputs are 1 and 1, and when you change them to 0 0, first there will be indeterminate state, and second, after changing to 0 0, it will break into oscillations, which is something which we don't want. Now the previous approaches, the level sensitive SR latch and later on the D latch, it actually eliminated this problem by avoiding the existence, avoiding the appearance of 1 and 1 at the input. But JK flip-flop is again a refinement in the sense that even if these inputs appear at the basic latch, they will be defined. It won't be an indeterminate state, it will be a determinate state. So let's look at the circuit first. Again, I have the basic SR latch here. I am using the NOR gate, so we're continuing with that. So here are the two NOR gates, and then I have the feedback connections. And the second input here, it will be fed from an AND gate. So I will draw an AND gate here. Similarly, like we had in edge sensitive, level sensitive SR latch. So here the second input, here is my second input. Fine. Then just like in the SR latch, where we had a common clock input, so it will still persist here. A common input on which we apply the clock. Fine. Then we have the external inputs. Here we call them J and K. Fine, so these are my external inputs. The upper one will be J, which will feed to, remember this is S, this is R, and the lower one will be K. Then there's a third connection. We have another feedback connection here. I'll be drawing it here. And that feedback connection is actually the third input of this AND gate. And it goes something like this. Q bar is fed back to the AND gate that feeds the S input, and Q is fed back to the AND gate that feeds the R input. Now this is the schema of a JK latch. Right? And let's try to understand the behavior. We know the behavior of the SR latch. S stands for set, R stands for reset. So let's construct a small table here wherein I will have the previous state or the current state Q of t, then different values of J input and K input. And then we are interested in finding what is the next value of Q. Like I said, we have two outputs, but we are mainly interested in the Q output. Now, if the current state is 0, current state of this JK flip-flop means it is a reset state. which means Q is equivalent to 0. We have to see for different values of J and K, what will be the next value of Q. So if I start with J is equivalent to 0, K is equivalent to 0. Let's see what the condition are. So Q is equivalent to 0. By definition, Q bar is 1. When Q is 0, one input of this AND gate is 0. K is also 0. Going to the upper AND gate, Q bar is 1. So this is 1. J is also 0. And this means this will be 0, this will be 0. And you know, in a basic SR latch, when S is equal to 0, R is equal to 0, your current state is maintained. So your next state is going to be equal to the current state, which is 0. Then again, if current state is 0 and J is 0, K is 1. Fine. Again, Q is 0, which means Q bar is 1. Q will be fed back to the K gate, but this time round, this input is 1. Fine. J is still 0. Fine. So this means, but again, since one of the input of the AND gate is 0, which means R will still be 0, S will still be 0. And the basic SR behavior is that when S is equal to 0, R is equal to 0, your previous state is maintained. So in this case also, it will be 0. Then again, if my current state is 0, J is 1, K is 0. Now let's see what happens here. Current state is 0, which means Q is 0. It will be fed back here, so this will be 0. Now K is equal to 1, sorry, 0. So I will change this to 0. And for the upper gate, J is now equivalent to 1. So this is a new thing here, 1. Now if you look at the lower AND gate, both the inputs are 0. Even if clock goes high, R will stay at 0. But in the upper gate, when the clock goes high, all the three inputs will be equivalent to 1. And when all the inputs of an AND gate are equivalent to 1, it means that the output of this gate is 1. So the basic SR latch, the core element will have S is equal to 1, R is equal to 0. And from the basic SR behavior, we know this is the condition for the set state. So now my next state will be equivalent to 1. Similarly, if my current state is 0, J is 1, K is 1. Now this was the condition that was creating problems in the basic SR latch. When both the inputs were equivalent to 1, our flip-flop, a latch, went into the indeterminate state. Now let's check here what happens. J is 1, K is 1, so this means my current state is still 0. So that persists. So one of the inputs will be 0. Now J is 1, K is 1, but in the lower AND gate, because of this feedback connection, R will still be 0. And in the upper AND gate, it will be Q bar 1, J is 1. So we'll have still the condition S is equal to 1, R is equal to 0, which is the set state. And in the set state, the next output will be 1. So this is the condition that has been defined now. This no longer is an indeterminate state. Similarly, if current state is 1 and J is equal to 0, K is equal to 0, you can work out the same process. Q will be 1, so the lower AND gate will have this as 1, but still K is equal to 0, J is equal to 0, means S will be 0, R will be 0. So whatever is the current state, that will also be the future state. Fine. Similarly, if QT is 1, J is equal to 0, K is equal to 1. Now let's work out this combination. Let me just... So as per this, my current state is 1. This is 0. This will be fed back here. So this is 1. K is 1. This is 0. J is 0. So upper AND gate will have 0. But the lower one, as the clock edge goes high, will have 1. So in the basic latch, S is equal to 0, R is equal to 1, corresponds to a reset state, and for the reset state, output is 0. Similarly, if I have 1, with this and this, your output, you can again work out the same process. It will be 1. And finally, when q is 1, j is 1, k is 1, which was the indeterminate state, you'll again see j is 1, k is 1. But because of the feedback here, it will still be 0, r will be 1, which means again I am in the reset state. Fine. Now from this we can create using the k map. We can come up with a state equation. Here is the k map. We'll quickly solve it. I will have j complement k complement j complement k jk. Fine, then we'll fill up this map. So we are the one. So this is 1, this is 1, this is 1, this is 1. Now this corresponds to jk complement, jk complement, and q complement. So I'll have 1 here. This one corresponds to jkq complement. So I think this one corresponds to j complement q, k complement q. So this one, and then this one corresponds to jk complement, and q. So this one. Fine. Again, you can combine it in different ways. So I can have one of the combinations like this, and then another one like this. And this will give me the state equation for the JK flip-flop where QT plus 1 is equivalent to JQ bar plus QK bar. Fine. And this equation defines my JK flip-flop or JK latch. Like I said, latch or flip-flop, it is defined in terms of the way it behaves to the clock. So this is a very important modification of the basic SR system, SR latch or SR flip-flop, in the sense that the occurrence of 1 and 1 at the inputs, it does not drive the circuit into the indeterminate state. Yeah, it does not break the circuit into oscillations. This combination is actually defined in a JK latch, and this is my equation, right? And then a modification of JK latch or JK flip-flop is what's known as a T latch or a T flip-flop. Fine. And the modification here is, so this is a T latch or a flip-flop. And the modification here is that instead of using two separate inputs J and K, in the J and K, we just combine them directly. So we have a single input T that goes to the upper AND gate, and the same input goes to the lower AND gate. Now we know for a JK flip-flop, we just derived the state expression that QT plus 1 is equivalent to JQ bar. When I say Q bar, it is at time T. Current state, and this is the next state. Please keep that in mind. So okay, JQ bar plus QK bar. Right? And for a T latch or a T flip-flop, J is equivalent to K is equivalent to T. So I will have QT plus 1 equivalent to T Q bar plus Q T bar, or you can say it is simply Q XOR T. Again, this is at time T. Fine. So if I draw the state table for this, I will have Q of T, then the input T 0 0 0 1 1 0 1 1, and my next state, since it's an XOR operation, it will be 0 1 1 0. So it actually means if your current state is 0 and the input T is 0, you will maintain that state. If the current state is 0, t input is 1, output will change to here next state will be 1. Similarly, if q is 1, t is 0, it will stay at 1, 1, 1, it will be 0. Fine. And if you look at this behavior, there's a very important generalization here that in this T flip-flop, this has the ability, I can say the T flip-flop has the ability to toggle. Toggle means change. This is the term we use with flip-flops, to change state whenever T is equal to 1. If you observe here, this is my current input, current state rather. So when t is equal to 0, your next state, you are actually maintaining the current state because next state is equal to current state. But for the combinations where t is equal to 1, your next state is different from the current state. T is equal to 1, next current state was 1, next state is equal to 0. So this is the property of a T flip-flop. Yeah, T latch, that every time T goes high, the common input, whenever it goes high, then the state changes, what we call toggles. If the current state is 0, t is 1, it will change to 1. Similarly, if the current state is 1, t is 1, it will change to 0. So this kind of a behavior we call toggle in flip-flop in digital circuits, right? So this is where this flip-flop gets name for from. So 2t basically stands for toggle change. So every time t is equal to 1, the next state will change, the state of the circuit will change. Fine. So this was all about lights and flip-flops. And the next part, if you remember that in a sequential circuit, we have a combinational part, and we have the memory in the feedback element. Now, our first part of this sequential design was to, discuss these circuits, come up with a circuit that can actually store my binary data. Fine. So we have done a lot of circuits which allow us to store bits, and you can actually combine. You see, the thing with memory is once you figure out how to store a bit, you can actually replicate the same thing to store multiple bits. For example, if I have a D flip-flop here, which is the most frequently used. See, this is the D flip-flop. Fine. It will, as you know, it will have a D input, the data input, and it will have the Q output, then a clock. So this allows me to store one bit. Now, if I have multiple bits, all I have to do is to replicate the same thing. This stores my one bit. If I replicate it 2 times, it will store my 2 bits, say D1 and D2 with a common clock. Fine. If you have more than 2 bits, replicate the same unit that many times and you will be able to. In fact, this is actually known as a register. So a flip-flop stores 1 bit, but if you combine flip-flops like this, use a combination of flip-flops, it becomes a register. So register has the capability of the basic register. It may have some additional functionalities, but a basic register has a capability of storing multiple bits. You must have heard about whenever we talk about microprocessors or computer architecture, we say an 8-bit register, a 16-bit register. These are basically combinations of flip-flops that allow you to store multiple data bits. Fine. Now that we have learned how storage elements are designed, the next step is to come up with a methodology that allows us to design sequential circuits. Remember, when we started combination circuits, we first came up with a methodology, a 5-step methodology. Then we used that methodology with some minor changes, and we designed a lot of combinational circuits. Fine. The sequential circuits will have a similar approach. Now that we have designed their memory elements, we will now come up with a general methodology that will allow us to design any kind of a sequential circuit. Right? That will take next time, the next video. But before we leave, you will have another assignment. I think we had done 6 to 7 questions. as a part of your assignment. So next will be, last time I told you to design a basic SR latch using NAND gates. The question 7 of the assignment will be to design level sensitive and D latch using NAND gates. Then another question part of assignment will be to design JK flip-flop and a T flip-flop using again NAND gates. And I will add one more, do a bit of survey on this. Question number 9. Come up with at least two other methods apart from the edge triggering that we discussed here, apart from the master slave configuration that we discussed here. Two other methods used to achieve edge triggering in flip-flops. Fine. So keep adding these questions to the assignment. These will be evaluated when we come back in the offline mode. So let's stop here.